Hi, I'm back again. Today we'll be looking at GIS data models, and this is how we define them. A data model may be defined as the object in the spatial database plus the relationship amongst them. Okay, so we continue. GIS data model, an abstraction or simplified view of the real world. Okay, so here we have the real world and we have a data model, meaning from the real world, you're able to come up with a model. GIS data includes spatial location and non-spatial properties. So this is how the GIS representation looks like. So this is from the Google map. Then that representation would somehow look like this. Objects or features are representation of the entities in data model. So for example, the fire hydrant, okay, which is this one, okay. This one is location, then rows, spaces, or straight lines connected at nodes. Okay, as you can see them. Okay, then the legs can be presented by a set of polygons. Okay, so I have some exercises which I'm just going to jump. You find them as you get the actual PPT. What entities may we represent as points, line, polygon, or surface? So points, we're talking about buildings, the fire hydrants, location of accident, traffic, signals, and etc. Then when talk of lines, we're talking about roads, pipelines, rivers, those ones are going in straight line. Then polygons, we're talking about land parcels, lake countries. The surface, we're talking about elevation and temperature. Okay, so selection of data type also depend on the map scale. For example, how to represent building in a map, points or polygons. So map we'll do it like this. Then as points, we'll add it like this. And then coordinates and attributes are used to represent entities. Okay, so these are coordinates. Get a piece of land, they will actually put them in coordinates. Okay, attribute data type. So we have qualitative and also quantitative. So quantitative is numerical. Okay, so under qualitative, we have nominal attributes. We're talking about names or labels. So they provide descriptive information about an object, color, type, city, and name. Then ordinal values assigned to objects or events represent the rank order. So it may be either descriptive or numeric, okay, small or medium. So quantitative, often recorded as real numbers, most often on linear scale. Then interval, numbers are separated by the same interval. So the 0 point or the interval scale is the arbitrary and negative value can be used. Ratios have all features of interval measurement and also have meaningful ratios between attribute, physical player, quantities, or length. Representation of feature, okay? So we have the fire hydrant here, okay? The thematic layers will be represented as in this. I'm sure you can see how these layers are coming. So this is what we call thematic. Then data representation, this is discrete or maybe continuous. So discrete, then this is continuous. So this is how we represent them. Okay. So discrete. So reward entities are abstracted into three basic shapes. So we have retail stores from this map, land use, and also streets. So retail stores are represented with points. Then streets are represented with lines. Then land use, we use polygons or areas. Then when we talk of spatial, we're still talking about continuous data. So data is organized into surfaces where one attribute value across the surface. Example, elevation. Okay. Data types, models. So we have a vector data model and also raster. So when talk of vector, edges and verticals are defined by series of coordinates, x and y, and are connected by arcs. Then raster, we're talking about maps area divided into grid cells, and then each cell contains a categorical value. Model, this is data structure. So different types of data structures can be used to represent the same model. Example, consider a feature represented as a line, the vector data model. So to draw and analyze this feature as a line, computer needs some information, location of nodes. So this information can be provided in the form of a table listing, the coordinates of nodes, and also identifying which lines go through which node verticals. So this table is the basic structure coverage of this type. Data model of this structure will continue. So different types of data structure can be used to represent the same. I think I've already tabled this one. So representing the Earth. So this is how vector will look like. So first they have the real world. So this real world will be put into vector. Okay. Then you can also represent this one into a raster. Vector formats are discrete representation of reality. So it will come as like this. Then raster, we use square cells to model reality. Comparison between the two. Vector, we're talking about point here, position, no area, then raster, one cell. Then line, length, no width, and multiple cells joined at edge or corners, usually with 1 and 2 neighbors. Polygon area and perimeter, maybe it's contiguous. Okay. Vector data model. A vector-based GIS is defined by a vectorial representation of its geographical data. So in vector-based model, geospatial data is represented in the form of coordinates. So in vector data, the basic units of spatial information are points, lines, arcs, or polygons. So composed of two components, the one that manages the spatial and the one that manages the thematic. A unique key element called identifier for each object allows the system to connect to both database. Stores only those points which define features, and all space outside feature is non-existent. Vector data model. Okay, we continue. Some common vector formats. So we have coverage, shapefile, geodata space, TNT, triangular irregular networks, so like this. So what are the advantages of vector data? So it has a good representation of landscaping or landscape being mapped, looks great. Generalizing over graphics is possible while still maintaining the great looks. Then topology can be completely described in the network linkage. So raster vector, okay, you can tell from this. Then we come to raster models. So it has larger cell size, and you also have smaller cell size, and these are how they are actually characterized. So larger has got lower resolution, then the smaller has got a high resolution. The larger has got a lower feature spatial accuracy, then the smaller one has the accuracy, which is higher. The display for the larger is faster, for the smaller is smaller. The processing for the larger is faster, for the smaller is slow. The smaller file size, it has a smaller file size, other than it, a larger file size. How to represent features in raster, okay? So lines, then you've got raster line feature. Okay, continue. So for raster model, there are array of pixel. So each pixel representing a specific value. So a matrix consists of rows and columns with each grid or pixel representing a specific value. Okay. So cell values can either be positive, negative, integer, or floating point. So integer values are set base to represent discrete. Then floating point values to represent continuous surface. Then cells can also have a no data value to represent absence of data. So effects of resolution, you can tell from this picture, looking at the bigger the pixels, the better the quality, the lower the pixels, we can see how distorted the images are getting. So data accuracy cells, value is correct when the variable is uniform over the raster cell. In case of within cell variation, then average central or common value prevails. If we have this here, okay. Types of raster. Semantic raster. Like a map, describes the feature and characteristics of an area and their relative position in a space. Cell values are measured quantity or classification of phenomenon, either by integer, raw numbers, and stored in a single band. Image raster. Cells represent reflected or emitted light, as we can see from these images here. Okay, so rasters as a base map, this is how they'll come. Then as a surface map, they'll be like this. As attributes of a feature, they will look like this. Okay, and table like this. Then zone and region, cells with the same value markup zone. The size of the zone is defined by the count, okay, item. So a set of contiguous cells with the same value, okay? So this is a cells raster. Then this is how the overlay will actually look like. So forest, and these are the presentation. So when these are multiplied, forest and resort will have these as results. Then there we go again. Then we get this. No data value represents missing or unknown information. So when the cell is vacant, it's assigned a no data value. So no data value remains always no data for SQL users unless specifically requested. So acquiring raster data, remote sensing, aerial imaging, and others. Then data sources can be, so our data can be obtained from uh, digitizing existing maps, scanning existing maps, digital photogrammic map production, or entry complete coordinates from the field measurements. Advantages of raster data formats can represent different types of continuous surface and ability to perform surface analysis. So computing processing is faster, surface data is faster to display, then overlaying maps is easy, integrating of remotely sensed imagery is straightforward. So in short, it has all the good advantages that you might actually look at, but it also has its own disadvantages, which are spatial inaccuracies due to the limits imposed by the raster dataset dimensions. Then very large datasets need more memory space and more processing time. Okay, I mean changing cells to 1/2 current requires as much as 4 times the storage. There is no loss precision. So this is how we now represent this using the soft precision graphics in raster, Seno, in vector, traditional category in raster. Okay, so go on data volume, topology. Okay, so these are the advantages and disadvantages of raster. Conversion between raster and vector data models. Okay, the raster view of the world, the happy valley spatial unities, the vector view of the world. So this is how things are actually happening. Raster to vector, vector to raster. So this is how things move and the changes keep coming. Spatial data conversion to raster or rasterization, raster to vector or vectorization. Okay. Problem. If a cell is too large, 2 or more vector points may fall in the same cell. To avoid this problem, a cell size is chosen having the diagonal dimension, which is smaller than the distance between the 2 closest features. Conversion of vector files. So assign a cell as occupied by the line, okay, which is a near cell, okay. So conversion of lines is done like this: assign cells occupied by, okay, and this is how it will look. The conversion of vector area feature. So boundaries among different polygons identified as a vector to raster. So you assign the cell to the area if more than 1/2 is within the polygon, or assign raster to an area within the path. Then interior regions are then identified. Then each cell in the interior region is assigned to a value. Then raster to vector, which is R2V, point, line, or area features represented by raster cells may be converted to corresponding vector coordinates. Okay. Then the quality coordinating features, the quality and resolution of raster images are key factor for the quality. Okay. So we have a raster here. Then from this raster, we have the cell center points. Then eventually we have the smooth line. Okay. And you can see from here, our smooth line. So each raster cell is assigned an attribute value. Then boundaries are set up between different attribute classes. So a polygon is created by storing X and Y coordinates for each point adjacent. So here is our example, vector and raster. So in ArcGIS tools for conversion will work like this. So we have a toolbox, toolset, and this is how things are placed. Okay, so basically on the GIS data models, this is what I had for you. This has been Preston Winga. Till next time, bye.